Hello. In this podcast, we're going to look at the double slit, moving a little bit on from what we looked at in the core and combining it with work on the single slit that you've recently completed. So this is interference. This is 9.3 from wave phenomena, which we've split into three sections: Young's double slit, which we'll be looking at now. Then we'll go on to look at more slits, diffraction gratings, and thin film interference. So from 9.3, these are the understandings: Young's double slit, modulation of two slit interference with one slit effect, describing that qualitatively, how to investigate experimentally, and sketching and interpreting graphs that we'll look at more at in a question section to follow. So in the core section, we looked at double slit interference. This is known as Young's double slit. So let's just talk a little bit about Thomas Young. He was born in 1773 in Somerset. He went to university in Edinburgh and then in Göttingen in Germany, learning medicine. And he was a great polymath. He was elected to the Royal Institution and appointed as a professor at the young age of 27, I think. And then by the time he died at the sadly very early age of about 56, he was a member of the National Academy of Arts and Letters in not just Great Britain, but in America, in France, in the Netherlands, etc. He was a great polymath. He worked in several areas. He worked in medicine, obviously. He was a doctor. He worked as a doctor. He made discoveries relating to engineering, tuning musical instruments, Young's modulus in engineering. He made a great decipherment of Egyptian hieroglyphics. He was a competitor to Champollion, the French, who was the guy who in the end used the Rosetta Stone to decipher Egyptian hieroglyphics, but Young made great strides in that area as well. But he's perhaps best known for his work on light. Newton, in his great work Optics in 1704, said that light was made up of corpuscles. There was at the time there was a big debate amongst the leading scientists, as we would call them, as to whether light was made from particles of some kind or waves. Newton was for particles, and his great contemporary Christian Huygens was for waves. Thomas Young was definitely in the waves category, and he devised an experiment to demonstrate this, to prove it as he would have said. Of course, we know nowadays that the situation is a little bit more complicated. But what he did was he did an experiment, and it's illustrated here in his lecture notes from 1802. The bit encircled there shows a box, and into this box were two slits and another place where you could look through. And when you drew the two slits, he saw a pattern. Okay, so you can see here that from those two slits, and this is a photograph of a reproduction of that experiment, you could see a bright central white band and then various other bands sort of fading away, which becomes sort of more coloured as you move away from the centre. And this is a copy of Young's work at the time, and in here he says that a beam of homogeneous light, because this was done with sunlight, but by homogeneous light he went on to refine it and did light with single colours, falls on a screen in which there are two very small holes or slits, which may be considered as centres of divergence. So the idea is that the light spreads out from these holes. When they are received on a surface placed to intercept them, in other words a screen, their light is divided by dark stripes into portions nearly equal, but becoming wider as the surface is more remote from the apertures, so as to subtend very nearly equal angles from the apertures at all distances. So yes, the bands get slightly wider as you get further out because of the geometry, but the actual angles are pretty much equal. The middle of the two portions is always light, and the bright stripes either side are such distances that the light coming to them from one of the apertures must have passed through a longer space. This is again just going back to what you saw in topic 4.4, I think, where the light coming in, and it has, as he describes it, undulations here. So the light bands correspond where there is 0 or 1, 2 or 3 wavelengths, which, as we described at the time, means that there is no phase shift, whereas the dark bands have a half or 1.5 or 2.5 wavelengths. So there is a phase shift of pi radians or 180 degrees, which means you get destructive interference. So the light bands are where you have constructive interference, and the dark bands where you have destructive interference. Again, we went through the mathematics of this in that previous section, but the equation that we came up with at the time was S equals lambda big D over little d. So the S is the distance to the between the fringes that you observe, and it's dependent on the wavelength and reflecting the geometry of the situation, the distance from slit to screen, and the separation of the two slits. So that's Young's double slit. But what Young's double slit would seem to imply is that these bands should go on equally forever, and that's not what we saw. That's not what you saw in the picture just there. They do fade away. Okay, so you do not get an intensity pattern like the one that's on the screen. Instead, you get an intensity pattern that looks a little bit more like this, with, yes, a most intense band in the middle, and then the bands get weaker as you move away. And the reason for this is because of the effect of single-slit diffraction, which you have just looked at. Because in reality, those two effects combine. See that nicely in this image here. You have the double slit, the interference pattern between the two slits, which is this uniform set of waves. And then you have, due to the width of the slits themselves, this single slit diffraction pattern, okay, with much broader minimum. And illustrated in red here, you can see that you have the combination of the two, which means that with this particular arrangement, with a slit width of 2 wavelengths of the light and a separation of 6 wavelengths of light, that the maximum at m equals 3, m is the order, so 0 is the central one, and then 1 is the one to the side of it, 2, 3, 4, etc. The m equals 3 is actually completely missing, because at that point the single slit diffraction completely goes to 0 and negates the double slit interference. So you have the two equations here. On the right hand side in the green, you have the double slit equation, which you saw in the core in topic 4, and on the left you have the single slit envelope. I like that way of describing it. It's the envelope which constrains the double slit. On the right hand side of the equation, you have distances. On the left hand side of the left equation here, the single slit envelope equation is more about the angles. But these two equations, or combining these two equations, will enable you to answer basically all of the questions that you're going to need to answer. You don't need to have an equation to draw this line exactly, because the subject guide says describing it qualitatively. But that doesn't mean qualitatively without any equations. It just means that we stick to these two fairly simple equations. If you go onto the website that's shown there, and if you're on my website, I'll put a link to it. There's a good little simulation here which allows you to change the slit width, the slit spacing, and the number of slits, just 1 and 2 for this demonstration. But in future we'll be looking at more multiple slits and see the effects. If you want to experiment this, if you want to do this experiment and investigate it in an experiment, one way that Thomas Young did this to demonstrate his findings was using a ripple tank. So you put water in the tank, you create a physical barrier with slits, you have an oscillator, and therefore you can see what happens to the waves. Another possibility is using a pair of speakers, because this works actually for sound waves just as it does for light waves. Okay, and the experimental setup is there, and the Institute of Physics has a description of how to do that experiment. And then the other one, which you'll probably be seeing in the lab, is using a laser. So you have a laser shining through excuse me, shining through a slide. The YouTube site I've linked here, assuming it's still active, will go through the use of this video. And those slides, you can see the slide on the left hand side, that's a standard school lab equipment, and they have 4 examples of slits, all of which have a width of 0.15 millimeters and have separations of 0.25, 0.50, 0.75 and 1 millimeter. And that's the kind of pattern you would expect to see. Bottom left, again, the overall, the envelope, so to speak, is provided by the single slit diffraction, and then within it you have the double slit interference pattern. Okay, so we've discussed Young's double slit experiment and Mr. Young. We've discussed how the 2-slit interference is modulated by the 1-slit diffraction pattern. It provides the envelope there, and we've shown how to investigate that experimentally. And then in a following video we'll look at a couple of questions on how to do this.